All right, here at 6, it is Tuesday. You had a nice 3-day weekend. You probably spent it just like I did, sitting around yesterday, honoring the office of the presidency. Good, which has brought us nothing but honor without exception. But now we are back in school, and snow is coming, and ice. Rumi, are you excited? Good. So I think that there will be no period 4 tomorrow, and since there will be no period 4, I believe that we are taping this class so that they can watch it. Sound good?
Good.
Okay, so here's where we are. On the first day of this class. First day of this class, we pose 2 problems of calculus. And both of those problems involve infinity in some kind of a way. And then, as I said would happen, we took a 2-week detour into becoming experts on manipulating infinity. And the mechanism for that is this thing that we call limits. So we took it pretty seriously. Like, we did a lot of limits. We defined even precisely what a limit means. We sort of defined it away, you might say, as being a statement about things, small things existing in small intervals between other small things. And we got really, really good at limits, and we did a million limits, and we learned the squeeze theorem and all kinds of other special facts. Do you feel like we're kind of done with this? I feel like we are. Good. This unit's over. Then we had a quiz on Friday. We'll pass that back later. And then you had a review packet. The review packet is like pretty hard, right? I thought. How's it going? Ish.
Good.
Some people say not too bad. You think it was like challenging? Good. I'll be after school today, as I am every Tuesday. And anyway, the test will be like not this week. It'll be next week. So I think we should start the new unit. Are you ready?
Good.
Woo! Good is not a response to are you ready? What? I will put up an answer key closer to like after it's due. Okay, today's an exciting day because what we're going to do now is both attempt to solve and pretty much within about 10 minutes just straight up solve one of the 2 problems of calculus. Whoa. What? Yeah, that's right. What were the 2 problems of calculus? Yeah, give me one.
The tangent line problem.
The tangent line problem, and that's the one we're going to solve, so let's just start. All right, what is the tangent line problem? There's actually many different ways to answer this question. What is the tangent line problem? What's one? What is it? Yeah, what is? Give me a geometric answer to what is the tangent line problem?
You have a curve.
Daphne.
You have a curve and you have a line, and you want the line to intersect the curve at one point.
You have a curve. Say it again.
And you have a line, and
you have a line.
you want the line to intersect the curve at one point.
I think it's a little bit more specific than just you have a curve, you have a line. You have a curve. The tangent line problem sort of is the problem of doing what? At a particular like x value. Maybe that's what you meant, right?
Yeah.
But yeah, at a particular sort of point on the curve, I think is maybe the best way to say it, right? Never mind the x-axis, that's like lame. Given a curve at a particular point on the curve, the geometric way of stating the tangent line problem is find, construct is probably the way it would have been said, once upon a time. Construct the tangent line to the curve at that point. And by the way, what's like the one curve for which this is like trivially easy because of like geometry? Circle, yeah. If you have a circle and someone says, and the center of the circle's here, and someone says, find the tangent line to the circle at this point, how would you do that? Yes, shout it all out at once.
Perpendicular.
Perpendicular, yeah. Whoever said just perpendicular, that is correct. It is a fact that the tangent to a circle is perpendicular to the radius drawn to the point of tangency. And so for this one particular case, it's quite easy to construct a tangent line, a line which touches the curve at just one point. But for some arbitrary curve, like a cubic function or a cosine function or a logarithm function or something like that, then this seems like harder. There's no obvious way to do this. This is the tangent line problem. Given an arbitrary curve, find the slope, find the tangent line to the curve. Okay, can we step back a little bit and ask the whole why question? Like, what does it mean? What is the point why did I want to solve the tangent line anyway in the first place? There was like a reason, or at least I gave a reason. Whether this is the like historically accurate reason or not is something I will
It lets
address.
you find the slope at one point.
I agree that we want to find the slope of this line, but
Like
why?
at one single point, one instant, one point.
There's a key word you gotta say.
So
Some
you
people
know
just
where-
mumbled it. Everyone shout it out.
Instantaneous.
Speed, yes, speed, yeah. Yeah, this is sort of like is gonna tell me the speed, I guess. If this is a position versus time curve, in other words, if this is a curve that will tell you at a given time what the position is, then we think that somehow that at time A, the slope of this line will give us the speed at that exact point. And why? Well, I guess we should just return to what we did on the first day of school, which was only like 3 weeks ago or whatever, 3-4 weeks ago. The first day of the semester, I should say. And okay, if this is a position versus time curve, then the way we introduced this was to say, all right, take this time A, and now take a time which is a little bit more than A. Let's call it, I don't know, X. All right, and let's let this function be, let's call the function F. And so here's what this position versus time curve is telling us. It's telling us that if I go at time A, that the position of the object will be at F of A. Cool? And at time X, the position of the object will be F of X. Okay, and now we can ask a very natural question, which is what is the average speed on the interval AX? And the answer is, just by the sort of definition or conception of average speed, that it's just going to be the total distance over the total time, yeah? Okay, and what is the total distance traveled during this time interval?
X minus A.
It's just like the change in position, right? I'll even write total distance over total time, and the total distance is f of x minus f of a. Yeah, and the total time is x minus a. And the picture is like not needed really in any way for this, but the picture does add a little bit of a geometric flair to what's going on, because this, if I sort of drop perpendiculars down and over from these 2 points, then it's like natural that we have this kind of a triangle. So the change in the position is the difference in the y values of the functions between those 2 points, and the change in time is just the x interval, the length of that x interval. And so this average speed we associate with the slope of the secant line. And this thing, I think I used this word already, right? On the first day? Secant line. The secant line is given a particular function and a particular interval of inputs. Then the secant line is just like the line through those points on the function. And the slope of the secant line gives you the average speed on that interval, slope of secant line. All right, so this is all kind of like review. And then we said, what if I want to know the exact speed at time A? What should I do?
2 points that are like infinitely close.
Make x really, really close to A is a good way of putting it, right? The closer I move this point x to A, the smaller an interval I am sort of taking the average speed over. And what we in fact concluded from this whole conversation about speed guns and stuff like that is that really the very concept of instantaneous speed kind of rests upon the idea of taking an average speed over like an infinitely small interval. And so if I can somehow move these 2 points sort of infinitely close to A, then this is the tangent line, then x just becomes A. Okay, so this just, the answer is just obvious. What is the slope? What is the slope of the tangent line to f at x equals a. How can we find it? We're just, use limits, right? Limits are just kind of this formalization that we constructed to deal with infinitely small things. What we just said out loud, which I think Katie said it, but I think some other people were saying it also, is that if it's the slope of this tangent line that I want, the slope of this line is going to be the slope of whatever the secant line is when x is like as close to a as possible. And so I take the slope of the secant line, f of x minus f of a over x minus a, and what should I do?
Limit as x approaches a.
Take the limit as x goes to a. Whoa. Whoa. That's it. Tangent line problem solved. If you want to find the tangent line to a curve at a particular point, then just take the limit as x approaches that point of the slope of the secant line. Okay, and sort of before we even do an example problem, I want to introduce you to some sort of flexibility in notation. This notation which I've used is kind of nice, but sometimes you also want to use a different notation. So here is this, so same problem, same function or whatever. I also have a point A, and it's also true that this is the point A comma f of a. But maybe instead of calling this second point x, because the whole point of x is that it's supposed to be really, really close to a, right? So maybe I want to call this other point a plus h, where I think of h as being something very, very small. And if I do that, then this point is a plus h comma f of a plus h, so on and so on. And now I'm making the exact same arguments all over again from before. No difference. What is the change in the position f of a plus h minus s of a, and what's the change in the time, just h. And so if I want to find the slope of the secant line would be, well, it would be f of a plus h minus f of a all over h, right? And if I want the slope of the tangent line, what should I do? Everyone's all shy and quiet. What I should do is move the points infinitely close together, which is equivalent to saying take the limit as h goes to 0. Okay, cool. Let's just immediately do a problem. Here we go. We have sort of in principle solved the tangent line problem. Let's go. I will give you a function. Here's the function. F of x equals 4x squared plus 1. Find the equation of the line which is tangent to this curve at the point x equals 3. Go. Whoa. Good.
I just thought of this one.
Maybe small problem. I think so. It looks thicker than not too bad. Take a lot of notes.
I would play some gentle background music, but then Google will block the video. So instead, I will just sing.
Oh no.
But I only know baby nursery rhymes.
So we play royalty free then.
Yo.
I'm not going to be here on Thursday and Friday.
Yeah, you know.
Who's this for again?
free music. It's not working. It's terrible. Someone's dancing. Whoa. All right. So how's it going? I recommend doing like the sort of pictures are right here on the board, but I recommend making a kind of like a generic sort of picture to yourself, not particularly necessarily accurate. So the idea is, hey, given some generic function or whatever, here I am at x equals 3, and then, well, there are two ways to do it, as we've seen, right? There's the sort of way number 1, and there's like way number 2. So if you do it way number 1, then you pick a point x, which is like a little bit more than 3, yeah? And you get up here, and so this point would be 3 comma, well actually what happens when I plug 3 into this function?
37.
Yeah, I get 37. And if I plug x into this function, well, I get back 4x squared plus 1. Yeah? And so, turning this nonsense off. You like it? Okay, should we turn it? No. Alright. So anyway, what is the slope of the secant line through the point 3 comma 37 and x comma 4x squared plus 1? Well, I think it's pretty clear, right? You just take the y value here, which is 4x squared plus 1, minus the y value of this point, 37, over x minus 3. This is what you guys all did? And then this is the slope of the secant line. Well, to find the slope of the tangent line, what do I do?
It's big.
Take the limit as
X
x approaches 3. Alright, and this is like a, level 2 out of 10 limits problem. Like, it's just pretty easy, right? You guys are all experts on limits, so hopefully you'll get like the right answer. Before you, just for like practice and stuff, let's do it actually both ways. So if you did it this way, good job, finish up that limit. If you did it the other way, well, I would just like everyone to do it both ways, because you should be comfortable with both. So the other approach is the exact same logic, just the notation is a little bit different. Now we take this point 3, where we're trying to find the tangent line, but we call this other point, what do we call it? 3 plus h. And now, what's the slope of the secant line?
4 times 3 plus 8 squared plus 1 minus 37 over.
Yep.
I think you did that right.
I think you did. Yep. Ours says it's just the value that you get when you plug 3 plus h into the function, which she just called it out as 3 plus h squared plus 1, minus the other y value, because this point is still 3 comma 37. And now what I want to do is take the limit as h approaches 0. All right, so everyone do both of those limits. And you should get the same thing, right? So just do it both ways, and then write the equation of the line. Oh yeah.
This is like totally.
Royalty-free music. All right, did you get 24? Woo! Good. It's like I'm in a department store or something. Terrible like that. Alright, did you also get 24 for this one?
Yeah.
Yeah, it's like a little different though now, right?
Rose, how did you
What's up?
how did you get that equation?
How to get this?
Yes.
Because, so it's just the sort of logic of the problem is exactly the same, but just the choice of how we label the points is a little bit different. So instead of calling this second point x, I call it 3 plus h, thinking of h as very tiny. So now this point on the curve becomes 3 plus h comma whatever f of 3 plus h is. And that's the function, so I just plug 3 plus h into the function. Cool. Welcome. Minus 36 over h. And then how'd you guys do this? Did you just expand it out?
Yeah.
Yeah. Yeah, that's not so, let's, here, I'll do it down here. So you get like 4h squared plus 24h, like plus 36, but like then minus 36 over h. And then the h's cancel, so it's like 4h plus 24. But then we take the limit as h goes to 0, so it's 24. Woo! Okay, so we found that the slope of the line was 24. Before giving the actual answer, let's just like pause to reflect about how awesome this is. I know like this might not seem like that big of a deal, but like we just solved the problem. We just like suddenly like we can just do the tangent line. Like we've just solved the tangent line problem, at least for this function. What does this, now let's make a kind of an accurate graph of this function, or at least try to. This is the function I plug in 0, I get 1. I plug in 1 and I get 5. So maybe 5 is up here. I plug in 2 and I get something 17. So there's 17. I plug in 3 and I get 37. Okay, and now 37. Okay, and now I guess like whatever. Woo, there it is. All right, so there's a reasonably accurate graph of this parabola, and the question which like 20 minutes ago would have been just totally impossible for you to solve is, what is the slope of the tangent line to this curve at the point x, terrible tangent line, at the point 3 comma 37. And what we've just determined is that the slope of this line is 24, which looks about right. I mean, looks about right in the sense that, you know, I'm expecting a big positive number. So there it is. Whoa. Alright, what is the actual equation of the tangent line? Well, since it goes through the point 337 and has slope equal to 24, then the simplest thing to do is just write it as y minus 37 equals 24x minus 3. Is that what you did? Point slope form? Woo! Alright. Whoa is right. Okay, this is like pretty amazing. Good. Let's do another one. Or let's do, hold on. Okay, so that's pretty exciting. Yeah, let's do another one. Here we go. Let's take a function which is not a polynomial. Let's take the function f of x equals 1 over x. Find the equation of the tangent line to the curve at the point x equals 4. Go.
Are we doing both methods?
Yeah, try both methods. I need to get the new royalty music. Aaron, do you have any recordings of your band?
Or is it like something to move on?
Yeah, so I do the same thing every time, which I think is especially good for beginners to kind of just like reprocess the whole argument. I draw myself like a generic function f, never mind it being accurate or whatever, and then just like kind of talk it all back out to yourself again. What are you doing? What you're basically doing is you're taking the point 4, and then you're taking a point which is a little bit bigger than 4, calling it like x, and then you're finding the slope of the secant line through those 2 points, cool? And then taking the limit as those points become infinitely close together. X minus 4, and this is f of x minus f of 4. And then the other way of doing it is to consider the function f. This is 4, and instead of calling this x, calling it 4 plus h. Both are sort of convenient. How's it going? Ooh, oh, he's done. Try it both ways. Try to do this, try to find the slope both ways. Oh, you guys are just like done. Am I going too slow? Right. Alright, and if I had given you this limit like 2 weeks ago, you guys would have been like, oh, I don't know what to do, I don't know what to do. But now it's like, oh, come on, another one of these, pretty chill. In fact, this is a 0 over 0 situation, so what should we do? Yeah, good. On the video, note the entire class bursting out in unison with correct responses. Yeah, I will edit in boisterous responses from this background. Woo, yeah, woo! Get a common denominator, so that's like 4 minus x. Is this what you guys all did?
Yes, sir.
Alright.
Common denominator.
Yeah, common denominator, and then like,
You just gotta like flip the top.
yeah, and then you just like, yep, boom the cancel boom the, and then you get like limits x approaches for -1 over 4x, yeah? Did you guys get -1/16?
Yeah.
Woo, woo! What happens if you do it the other way? Did you do it the other way also?
Yes.
Woo!
Same thing.
Yeah, you also get the same thing. Let's do it now for practice. Oh yeah. Oh man, what should I do? Oh, I should get a common denominator again. Thanks, class. Well, these should be h's. Oh, this put the limit wrong. Just fix that. What is h approaches 0, of course. That's 4 minus.
Yeah.
So this is the limit to negative h over 4 h plus 4. H is canceled.
I know, but I don't care, it doesn't hurt.
-1/16. Whoa. Okay. Are you feeling like the power of calculus to just like solve all your problems? This is like amazing. What this means is our old friend 1 over x, which we've been graphing since like forever. If this is somehow like the position versus time curve of some object, then if I go down here to x equals 4, first of all, this will be the point 4, 1/4. Suddenly I can tell you exactly how fast I'm going at that point, as long as I accept this sort of abstraction that the instantaneous speed is the slope of the tangent line to this point, then it's very convincing based on examining the picture, and the math backs up that the slope of this line is -1/16. It's incredible. Whoa. And the equation of this line, therefore, to answer the question, is y minus 1/4 equals -1/16 x minus 4. That's the most efficient way to just write it using the point slope law. Okay, whoa. This idea comes up so often, this find the slope of the tangent line to the curve idea, that we have given it a name. We have called it a derivative. Dun 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 dun. Okay, so definition, the derivative of f
There was just like a total lack of example.
at x equals a, which we have a notation for. We call it f prime of a. This is the notation. Is just by definition this thing that we've just been doing. It's either the limit as x approaches a of f of x minus f of a over x minus a, or it's the limit as h goes to 0 of f of a plus h minus f of a over h. And you should just keep drawing those two pictures for yourself every time, and thinking about it geometrically is the way to know how to set up the limit. Okay, good. So now what we can do is we can sort of abstract away from the problem a little bit, and I can just ask you a generic question. Ready? Here comes the generic question. If I tell you that f of x is x cubed, now I can just be like, hey class, what is f prime of 2? And asking for f prime of 2 is just asking what is the derivative of f at 2. In other words, what is the slope of the tangent line to the curve at x equals 2? Cool? Whew. Rumi is either doing a lot of algebra in his head